So, Good afternoon, everyone. I'm Bogdan Andrus, and today I'll present you our work on UAV sequence-based cross-view geolocalization under edge constraints. Before we begin, I'd like to say a quick thank you to my advisors, Maxim Davidov and Roman Ryazantsev, for their guidance throughout this project. So here's our roadmap for today. We'll start with the problem definition and motivation, why the problem of geolocalization matters, and why it might be hard to solve. Then a visual example from a data set, that is, we have a clearer picture of what we're dealing with. After that, related work and the gaps identified in the fields. Then our research questions, the proposed methodology, including both inference and training pipelines, the data sets we use, our approach, and a summary with the next steps. So the task of cross-view geolocalization is to estimate a UAV's absolute position by matching what its onboard camera sees against georeferenced satellite tiles, so no GPS. There are places or times when GNS signals might be unavailable or unreliable, so visual geolocalization is one of the few viable options for autonomous navigation. We are targeting realistic scenarios, and that means we'd like to exploit the temporal nature of the data captured by UAV and not to ignore it. Also, we have to take into account the computational constraints on such devices and the quality of the captured images. In our specific scenario, we deal with grayscale imagery. The call to action at the bottom frames the rest of the talk. We need a system that is efficient in terms of localization accuracy and fast enough to be used on edge devices. This is what the matching problem actually looks like. On the left, UAV frame. On the right, the corresponding satellite tile for the same location. A localization system has to match them in real time. The visual gap across viewpoint, color, scale, and resolution is exactly what the system needs to learn to bridge. The problem of geolocalization is not new by any means. It started far back in the early 60s as terrain matching, which was basically a contour matching. Then we have visual odometry, SLAM techniques. They are widely used today, but they tend to accumulate an error over time, and absolute geolocalization is the way to reset the error. Visual place recognition is basically the same problem, but in different setting. The viewpoint isn't changed, same. And finally, we have cross-view geolocalization, which is also advanced by deep learning. SOTAM system designed mostly to get the best recall for any price, and the hardware limitation was not in the topic. Also, lots of work has been done in the fields of optimization. The field has started responding to the efficiency challenge with three main strategies: backbone downscaling, designing model architecture from the beginning such that it's more shallow or narrow. Knowledge distillation shifts the cost to training. A large teacher produces supervision signals that guide a student towards better representation that it would learn alone. And post-training model compression techniques such as quantization and structure pruning allow to optimize the model without retraining from scratch. Those can be used together. We don't have to stick with a single technique. So this is the core tension we're trying to solve. State-of-the-art models achieve excellent retrieval recall, but are somewhat impractical on edge hardware, oftentimes too slow or too power-hungry for real-time UAV deployments. Additionally, all of SOTAs I was looking at worked exclusively with RGB data, and we don't know how they behave with grayscale imagery. In regards of temporal information, it's used more and more, but still in its early stages. So our work asks how far can we push lightweight architectures with the right training strategies, and specifically, what actually works under a grayscale input, where the model gets less visual information to start with. We frame the work as three concrete research questions. First, how does sequence-based processing affect localization accuracy, especially when the visual input is already reduced to grayscale? Second, how much does model capacity actually matter for cross-view matching, and can compression or distillation preserve the discriminative representations that make it work? Third, and finally, can flight priors information from onboard sensors compensate when the visual signal alone is insufficient? These three questions drive all our experiment preparations. Sorry for that. Our approach is rather explanatory than committing upfront to a single fixed architecture. We treat each pipeline component, namely feature structure backbone, temporal aggregation strategy, geometric re-ranking, and flight priors as a configurable design variable and evaluate them independently and in combination. The goal is to map the accuracy-efficiency trade-off space across a range of configurations rather than optimizing a single point on the curve. Finally, critically, all experiments use grayscale input throughout. So let me walk through the inference pipeline. There are two stages of flying. Before flight, we pre-built an embedding database. Satellite tiles are passed through the backbone to produce georeferenced embeddings stored for a fast lookup. This is one-time offline cost. Online, during the flight, the UAV captures a sequence of frames. Each frame goes through the same backbone for per frame feature extraction. Those features are then temporarily aggregated across sequence, producing a single compact query embedding. Flight priors from onboard sensors, attitude, altitude, velocity, can optionally constrain or refine this aggregation step. The query then retrieves the top K candidates from the satellite database. Optionally, a geometric verification step re-ranks the top candidates. The final output is the location estimate. The training pipeline has two levels. The core loop at the top, the primary training objective, the frames and satellite tiles from cross-view pairs both pass through the backbone, and the contrastive or tripled loss drives matching pairs together and non-matching pairs apart in embedding space. Note that flight priors fit into the sequence aggregation step, enriching the query embedding with more context. The optimization strategies discussed earlier, we can apply to the backbone. We evaluate across three sequential data sets, each adding something different. Two of them are Chinese. We also decided that it would be good to make some experiments within a controlled environment. So we made a simulated data set. Correlation metric circle at K measures retrieval equality at different candidate set sizes. So location error in meters gives physical accuracy in the real world, and FPS on target edge hardware tell us whether the pipeline is viable for real-time flight. For feature extraction, we are comparing two ends of the spectrum and looking for what bridges them. High-capacity models, Dino style to visual transformers, and SAT-Dino, which is basically Dino that was pre-trained on satellite imagery, provide strong invariance to the extreme viewpoint and appearance shifts in cross-view matching, but are far too slow for real-time edge deployment. Lightweight models, on the other hand, satisfy the hardware constraints, but struggle with the domain gap, particularly under grayscale input where color cues aren't available. The central question is whether knowledge distillation can transfer enough of the teacher's discriminative structure that the student become competitive on cross-view matching, even with a fraction of the parameters and under the harder grayscale condition. And now about temporal aggregation, we compare across the full range from no aggregation at all through a simple average pooling to attention-based approaches, specifically to identify when the added latency from more complex strategies is actually justified by the accuracy gain. As for flight priors, the question is whether lightweight sensor fusion can compensate for a weaker backbone. If the aggregation step is enough to substitute for visual capacity that a heavier model would provide, that's fundamentally cheaper path to better localization. And to summarize, and I'll also say a few words about earlier results. We outlined a systematic component-wise framework. The key design principle is treating each part of the pipeline as configurable rather than fixed, which lets us map the accuracy efficiency trade-off space rather than committing to a single architecture. Looking ahead, the three priority directions are systematic comparison of backbone choices, end-to-end sequential optimization, and deployment over benchmarking. Many thanks for your time. Thanks. Thank you for your attention, and I'm happy to take questions. And one final thing I would like to add that regarding the backbones, from what I've tried, SAT Dyno, so basically Dyno version 2 trained on satellite imagery showed the best results, but it's a heavy backbone, and regarding the temporal aggregation, so I tried average pooling, and I tried also transformers and transformer attention provided with the better results. So that's all for now. Thank you.
I will start then. I'm curious why, for example, why it's important to emphasize the grayscale image. In my opinion, maybe even better naming would be one channel image, but not grayscale. But even if we have multiple channels, we can have just one layer fusing them, and after that we may have just one channel. So I don't understand why is that it is that much important.
So basically, all the state-of-the-art models I was kind of dealing with during the research, but you know how they behave on RGB, and when we're talking about basically image retrieval, the color information is a big part of what we have, and if we kind of reduce the dimension only to one and make it monochrome grayscale, basically, we lose a lot, and they don't. It depends, because basically Dyno methods behave pretty well under such circumstances, but let's say standard CNNs are not. They highly benefit from the color information. So and the specific UAVs. I know there are kind of UAVs that are grayscale, but they also have to have such systems to work well.
So the idea is that to apply also this say one channel also to satellite images, and to have a database of embeddings, or
yeah, that's one of the options. The other option is to leave satellite colorful, and that's what I did in my early trainings, and it showed kind of better results, as if I, in contrast, would make satellite grayscale as well. So I left satellite colorful.
Okay, so the database consists of colorful images, and the query image is encoded like from a grayscale, and then maybe you can say a few words about how you do matching, because you have like RGB encodings and also grayscale encodings. Maybe a couple of words about that.
Yeah, basically, even though I do. As the very first step, I transform colorful image into grayscale, but I still keep 3 channels, but all of them are grayscale. That is, I don't have to change the base architecture. The architecture I was based on. So basically, the base architecture is not changing. I just make 3 channels, and all of them are grayscale. So there's no particular adjustments needed in order for that to work.
Okay.
I have a related question. Look, actually, a typical satellite image is not three-channel. For instance, AMIT has about 300 spectral channels, and Sentinel-2 has 28 or 30. Yes, so there is no RGB channels in Sentinel in satellite images. So that's why even grayscale matching can be problematic, because if you convert these spectral channels into grayscale, you can have different intensities for ideally matched images.
I got it. So yeah, one note here. I haven't note with haven't worked with satellite images directly. So basically, in all of the mentioned datasets, the tile was provided as some kind of PNG image or so. So I haven't encountered that highly dimensional representation that you mentioned. But that's interesting.
Yeah, that's the whole direction of super resolution.
So the caveat here is that usually, like, the more channels we have in the satellite images, the lowest resolution it is. So the highest resolution we may have for RGB because it's cheaper. And we can even have that if we have it's called multispectral images. So each channel may have different resolution, and
Yes,
some techniques can be applied to kind of resize or rescale to a particular. But okay, so
it's called hyperspectral super resolution.
yes.
Okay, but a related question is that's natural approach to take into account spatial sequence of frames you get from the moving drone. Yeah, but do you also use the information from the sensors, onboard sensors, to kind of predict the next location of the drone, and then have a guess, and then only fine tune it?
Yeah. So I've tried to enrich satellite embeddings with the actual position in. I don't remember how the coordinate system calls. Probably something like UTM.
Yes.
And I only enriched satellite embeddings because during inference time we don't know the actual position of UAV. So during training, I constructed a pair, one from UAV, just embeddings, and one from satellite with enriched embeddings with that encoded information about the location, and it showed kind of better results. It's fairly fine. Yeah, so I enriched the kind of the embeddings get straight out of the backbone with some additional information.
Yeah, my question was actually whether you can predict the next trajectory and use that to improve the localization. And also you mentioned that you can have velocity from the sensors. You have accelerometer, which measures not the velocity but the acceleration, and gyroscope, which gives you orientation, but not the velocity.
Okay, and about the prediction of location, I haven't tried that.
That's natural. It's when you take spatial, temporally ordered sequence, then you can use it to predict the trajectory.
Have to think about that. Thank you for your comments.
Okay, so it's time. Thank you, Bogdan. We move on to the next presentation. It will be delivered by a staff PowerPoint. And his work is entitled Motion Guided Detection of Tiny Objects from Moving Cameras.
Okay, so I'm glad to be here to present my position paper topic named as was presented motion guided tiny object detection from moving cameras. This was advised by Mark-Jan Kostyuk, and I will continue with this plan. It has a pretty standard structure. But first, we will talk about motivation and our research goals. Okay, the motivation contains three-folded problem. They are coupled like this. Ego motion, it contaminates every pixel that is recorded by our cameras. And the depth variation recorded by the cameras breaks planar homography assumption that every object, whether it is static or dynamic, it is not at the same depth within this scene, within the frame of the camera. So it produces parallax residuals after even compensating with a planar homography. So we cannot extract like true object motion. And the last problem that I found to be the most impactful in this scenario is CNN downsampling that destroys features of objects, especially around 32 by 32 pixels of area. This area was selected by choice because 32 by 32 is less than, it is exactly 1% of frame size at input size of HD frame. So in this position paper, I considered the input sizes of that were produced by the camera to be of a HD size. For this, I reviewed 35 methods from 2020 to 2025. And they address these problems in isolation, essentially. So only 3 of them achieve like partial coverage of all 3 problems. None of them addresses 3 of them simultaneously. So the goal is to design a temporal fusion framework that handles these 3 problems jointly. And I evaluate across CNN and transformer and backbones. And employ different fusion mechanisms, for example, conf GRU or cross permutation, to use the temporality of the frames and address those problems. So yeah, here are the problems visualized. All of them address different nuances and peculiarities of camera recordings, especially from UAV. I mean UAV because all these problems are especially mm, produced by the footage from UAV, and it was convenient to study those problems, whether in isolation or in like joint framework, because typically the footage from UAV it is shot from a far distance, and it is shot from a top-down view, so it inherently has object motion like from people or from vehicles, and it also has static motion because of parallax from buildings that we inevitably see at different depths. Okay, and feature degradation is just a special characteristic of how CNNs work, and the CNNs in question are the most usually used in production for analyzing UAV footage, and essentially every other footage, every other type of footage. Here is the table summarizing the problems that I have discussed. And related work presents the following structure, following missing gaps of every category of reviewed paper, addressing one of these problems or multiple problems. So we can see how rigid geometric methods they target just using classical CV methods to compensate for ego motion of the camera, not compensating for any depth variation, etc. Also, flow and motion guided methods, they may cover all three, but they lack supervision on fusion, and they pretty much describe how the models they do not use that much of supervision from machine learning methods. And other three categories, they also have poor coverage, like for example attention, like stacking or architectural preservations. They address P3 only. P3 is feature degradation from stacked layers. Yeah, so I will proceed with this research. Yeah, we have two levels. One is motion compensation that uses non-differentiable homography. So no gradient flows through the alignment. So we cannot produce at the subsequent iterations, we cannot produce a better flow maps to as a result produce finer refinement and alignment to get rid of the parallax artifacts or ego motion artifacts. And the second level is temporal fusion that uses, for example, fixed concatenation or averaging. So no signal tells the network where to trust each frame. It just tells us like whether this frame was useful for final detection of for about like 200 detections per frame. So it cannot tell us what part of frame was useful given the motion characteristics of the objects within this frame. So GAP is learned fusion with auxiliary supervision that provides per pixel guidance. So learned is we learn how to better fuse just the regular frames and motion with, for example, motion can be computed as the standard optical flow operation. Research questions is as follows. Thus, compensation plus P2 head beats single frame. P2 head is just an addition of standard feature pyramidal network that is used across the architectures of CNN. In question, like the one problem I mentioned before is P3 problem, which targets CNN feature degradation, and P2 head addresses exactly this because P2 head operates at lower strides, so it produces finer granularity per frame. Next question is, does learned fusion with auxiliary loss beat fixed aggregation? And the last one is, do benefits hold across backbone and fusion mechanisms combinations? Hypothesis emerged from the stated research questions is first one is auxiliary supervision auxiliary supervision provides better gains on tiny objects, and where single frame appearance is insufficient. So we cannot use just single frame as was presented in papers of one of the categories named architecture preservation that focused only on single frame appearance first. And the second hypothesis is the benefit is architecture dependent. So it should work, this auxiliary supervision with learned temporal fusion should work for both CNNs and transformer backbones. Here is the visualization of the proposed staged ablation framework. The first stage is just a single frame baseline for our CNN or transformer backbone. Then the addition of P2 head, which would be absent for a transformer backbone, to be honest. There is no such mechanism. And stage 3 is just an alternative for a single frame baseline. It extends the single frame to multiple frames, but it doesn't implement anything other than just sending the whole frame through the backbone architecture. No adding of any other architectural variant. And stage 4 is tree alignment variants. Sparse flow, dense flow, and flow plus refinement CNN to smoothen the edges of the produced motion map. And stage 5 incorporates stage 4. Stage 5 builds upon the best stage 4 variant. It means that like our proposed learned fusion framework is a 2x2 design, which can cross backbones with fusion mechanisms. Each comparison isolates exactly one factor, one added factor. For example, in stage 4A, as will be discussed here, stage 1 is just the true baseline. Then we have adding of P2 head. Stage 3 is 2 frames or 3 frames, previous, current, and next frame, shared backbone, and all of the steps performed with no alignment. So it tests whether raw temporal information has value without geometric compensation. Just the stacking of extracted features from the frozen backbone. Then these stages incorporate like sparse flow, dense flow, and flow plus refinement, as I said. For A and for B, they are exactly the same, except for in dense flow for B stage, we replace, for example, Lucas Canada with some pre-trained dense flow network, and we can replace RunSec with some alternative like IRLS for better GPU performance. Yeah, okay, sorry, I forgot to go to that slide. And yeah, here is the more visualized version of stage 5, exactly specifically learned fusion stage. And we can see that auxiliary loss is added as a weighted version to the detection loss. So we will not exclusively use only one of them. So we will use both of them at the same time to guide the detection bounding boxes and guide the temporal the quality of the fusion per pixel. The evaluation plan is based on two data sets and several metrics. Yeah, they are pretty large, as you can see here. Both of them exceed like 100,000 frames for training. And we can see that the scenery is rather variable for both of the data sets, and both the lighting, the point of view from which the drones were shooting the footage, and the objects are variable to object sizes. Yep. So the early results for this position paper only, and they contain the systematic review of 35 methods across within this field of studies. Then we have proposed the 5-stage ablation framework, and for stage 1, for stage 0, we composed PyTorch data pipeline to integrate those data sets for backbones. We presented different configs to flip and swap different modules within the stage framework, and we deployed the data to the remote machines. So this, for example, this video captures how the pipeline in action works. On the overfitted version of our ARD100 dataset on stage 1. So it is just the true baseline, and as we can see, the middle frames show the extracted motion with simple Lucas Canada, just for reference to see where is the drone and where and how does the scenery change affects the motion, just for the next stages. So yeah, I thank you for the attention, and will be glad to answer any of your questions. Thank you.
We have time for one question.
If one, then why 35? Why
I
not
got bored.
4? Sorry?
I got bored. I got bored.
You said
one question.
yeah. You said homography is not differentiable, but it's just least square problem. Why not differentiable?
It is not differentiable in the sense of how the people implemented.
But it's least square.
Yeah.
Why not differentiable?
In the sense of OpenCV methods, we cannot implement, for example, RenSack for it to be differentiable.
How RunSack can be differentiable? I don't understand. RunSack is just
but for us to compute the correspondences, we have to use RenSack. It is one of the methods. And RunSack is implemented in OpenCV, and OpenCV doesn't have a computational graph built for all of the operations. And it breaks the chain of for the backbone to be able to trace the gradients back to the homography alignment. And the OpenCV RenSack implementation, which is used by almost every study, it cannot be the gradients cannot be computed for this step, and it just breaks at this point.
Okay. And also one remark: you are using you're talking about fusion, sensor fusion. So you are using IMU, for instance, and barometer on board. Yes. So you can actually, from the barometer readings, you can calculate the change of altitude, and that information can be used to improve homography.
It can, but the modalities presented in the data sets that I have specifically researched, those data sets do not incorporate such data as IMU-based measurements. They only incorporate RGB footage.
But that sounds strange. Excuse me. Your task is to detect the motion of tiny objects from flying UAV.
Mm-hmm.
So you have to use the information about the UAV motion. And you are saying that the only data set we have, or our approach, will not use it. Am I right?
Mm-hmm.
So it's strange. For me, it's strange.
But okay. Okay, I see. But
you certainly should estimate the ego motion of the UAV and subtract it from the predict the next frame and subtract the change of position, and then use the optical flow or whatever on the resulting frame.
But ego motion is rather solved problem, and it does not present any problem to us, because ego motion is easily subtracted from the frame, given the temporality of the frames, and given that we can pretty quickly estimate optical flow of the whole frame. So
you're saying we can. Are you doing that, or you're just saying that it's not interesting because we can easily do it?
We are doing it in the scope of this position paper.
Okay.
Thank you. The next speaker is Ivan Visitsky, presenting stress testing monocular wire for long GNS as denied bias.
So, hello everybody, my topic is stress testing molecular visual odometry for long GSNS denied UAV flights. Here we have some outlines. We will talk about motivation, method families tested, research gap identified, problem definitions, hypothesis, approach, dataset discussed as a part of approach, and early results and current progress, what I did with these research results in the diploma. So, motivation. As we know, the drone flights during the war of Ukraine become like one of the main stuff that we use for war, for dealing cheap and effective damage operations to our enemies, for our like surveillance operations to and etc. So oftentimes the spoofing and everything is a common topic, so we need to localize our drone somehow, and both retrospective localization when we try to understand where the drone flew in the past by its video footage, or real-time localization is actual tasks that need to be solved. And the monocular visual localization was chosen as it's like the cheapest and the most reliable and the widespread method as that is set on most of the drones. So there is like LiDAR cameras, infrared vision, different stuff, but most of the drones use monocular vision, so it makes the most sense and profit to research method related to it. Then the performance. Most of the methods that exist now, it is open source. I'm not talking about the closed source. They are tested on short flights, sub 5 kilometer flights without too much domain shifts. And they usually either accumulate drift, fail on low texture areas, or they just focus on one domain like city or etc. So they can be relied for like 10, 100 kilometer flights. So this was the motivation to explore this method, to stress test available solutions and to see what actually might work for long flights. So what was tested? One of the families that was tested is cross retrieval, which is absolute localization based on the satellite tiles and the drone image, and we try to match them and get the coordinates. It has a limitation in scope of that we rely on the pre-computed satellite tiles, so we cannot improvise our flight if we decided to fly this trajectory and this piece of map, we can only localize on that one. Feature matchers, they are better. They try to get the median motion of the features between the frames, usually, and they are good for whatever flights you have, but they need initial pose, and they don't perform well on low texture areas like forests and rivers, etc. Also, we have visual optical flow, SLAM, basic methods that estimate the velocity from which we can like derive our trajectory there. They often accumulate drift and they initialization failure. So if we don't have enough optical flow in our frame rate, they will fail. And also hybrid fusion methods that combine usually one or two or three families together through some fusion framework. And because of that, they are reliable, they are better, they are fail resistant, and etc. But they are hard to implement, and it's relatively new families. The open source paper, as far as I research, appear at 2022-23, so it's very new family and unexplored, I would say. So the research gap, the existing trajectories are either 1 kilometer flights or it's mostly for absolute localization because they don't have flights, but they have isolated frames that you can try to localize. No benchmark have 10-kilometer flights, or it's like on Chinese terrain that is not good for us in Ukrainian conditions. And also the domain shifts are underexplored. So most of the methods, they either focus on city and then just tell like we have like 90% recall and some accuracy, and it drops 20% on the fields, and they don't explore this gap any further. So research questions are the next. First, which method category degrades least over long distances? So like by itself with minimal effort from our side to adjusting. The next question is which failure modes dominate under weather, lightning, and terrain shifts? So when our pipelines fail action. And the last question is which baseline is stable enough to get as improved as baseline for the diploma and further researched and adjusted. So the hypothesis are the next. Is there a generalized improvement, like we don't have to focus on forest, rivers, and all separately? We can like find some generalized improvements that can mitigate failure on all terrains and all failure modes. Is there some hidden weaknesses that wasn't stated for long horizon flights? Because like if you test on 5 kilometers might be good, 10 kilometers might fail dramatically. And we tried to understand is there such failure modes that hidden? And also the low texture terrains will be the single largest contributor. So there probably won't be any distinction between flying around the forest or around the lake. It will be like low feature areas that will fail our pipelines. So what's the approach and what's the pipeline? The pipeline was chosen on the base of the simulated dataset as it's controllable in we can set basically whatever we want, the flight trajectories, the domain shift, we can daytime, altitude, whatever. So it is generated in Microsoft Flight Simulator using the generation script. So also it's good because I can share the script as Microsoft Flight images are usually copyrighted, but I can share script and it can be recreated and anybody can receive my dataset via script sharing. Method select will select only images, no IMO data applicable. The camera is mostly downward facing with 10 to 20 degrees forward angle. Because of that, some ground truth projection is used to actually understand where is the frame center is for the proper localization, because otherwise the drone will localize incorrectly due to this angle shift. Metrics computed is absolute trajectory error plus recall as a baseline. And also the low texture analysis of the frames are added, so we don't have to look every frame of every flight to understand how it looks. We can just look on the metric of the features quantity and understand if it's low feature frame or high feature frame. And about the dataset itself. It contains 320 flights, around 16,000 images collected through Microsoft Flight Simulator, 20 locations in Eastern Europe. So we try to close the domain gap and region gap as much as possible. Each flight is up to 10 kilometers, but no less than like 8. Contains 50 frames on average, and intra-frame shift is usually 200 meters. And I forgot to mention that the average height of the frames is set as 500 meters. Each frame has 1024 to 1024 resolution, so basically square, oblique, downward looking camera images, and systemic variations are included, which is weather conditions, for weather conditions, including clouds, rains, and snow, 4 times of the day. And all of these conditions are equally like spread inside of the dataset, so each of them are represented. All methods are evaluated as zero shot, so nothing was pre-trained. The only exclusion is absolute localization methods that required the tiles computation beforehand. And again, the absolute trajectory error and recall was calculated. So now let's look at the family methods and the actual methods that was tested. So for cross retrieval, mobile geo sample for geo transgeo and the blood was tested, but later, when I understood that most of the group research also absolute localization method, I decided to focus on feature matches and visual odometry. Also, the main criteria to selecting method was open repositories. So I need to be able to download the code and not try to recreate it from the paper, because a lot of papers state that they did something, especially hybrid pipelines, but they don't post the code, the repositories, and you cannot recreate it on everything. Also for feature matchers, as there was XFIP light methods that usually used for edge deployment, like Blue, Lofter, Roma, and Omnigo, like very famous and basic method. And for visual odometry and SLAM, Tartan Vero or SLAM and Rings Mono was tested. Some excluded methods are DPVO as it caused CUDA failures on my machine, Superglue also because of its license, and hybrid methods, as they mostly described as papers, have parts of pipeline not documented but posted on GitHub, but none of them have all of the code required to like just plug in, adjust parameters, adjust variations, and not try to reverse engineer the whole paper. So they was excluded. And here we can see the samples of the frames. So it's flight one, the slides that I will use to just demonstrate how the methods work and how they perform. So frame 15 is like rich feature frame where method perform usually well. And then we have low texture frames as fields and like also even less feature rich field. And now let's look at some results. Here represents only 3 feature match results as they performed the best in this category. So here's light blue. This method performs, as you can see, relatively precise for such a long flight, but its recall is like only, I guess, around 10% or 20% because out of 40 frames it recalled around 10. So, and also at the side you can see this gradient line which describes on which frame how much features was computed, so feature density of each frame. So the yellower or greener the frame, the more feature densities, the bluer the frame, the dot on the plot, the less feature densities. And as we can see, it skipped entirely the last feature poor feature region, it skipped medium feature region, and it mostly engages after feature-rich frames. So the next one is XFit. This method was adjusted to take more frames, more features, because originally it didn't perform well on the dataset. And as you can see, it performs better. It has better recall, but on the last piece, and also like the green circle is the top at the start, and the square at the bottom is the end of the flight. So we can see that at the last area of feature poor frames, it started to have tremendous deviation from original trajectory. And it kind of tried to recover, but still we see he has a gap at the end. So better, but still not good. And the last one is Lofter. It's has the most recall, but actually the least precision, because as it has more tries to understand more features, it makes more mistakes. It's like actually the nature of this method. So after analyzing all the flights, I understood that the no method like performs well on long flights. They either have poor recall or poor accuracy. Low texture frames are usually the only generalized metric I understood that the method fails. They fail absolutely the same on fields, forests, and lakes, so there is no distinction too much on it. Domain shift is also visible because during like from city to forest fields, the method is actually where they degrade. And also, all methods have a good tuning sensibility. For example, for XFit, the initial repo produced 0% matches to 75% recall. So it's actually pretty good. You can go a lot of the way with just parameters tuning from the methods. And actually, the direction of diploma. As far as I saw on my pipeline, the method can't recover after failing on poor feature areas. So the decision was made to take the hybrid pipeline that is the most documented, which is Static Fusion, that uses as much as ready solutions as there can be, so I can easily recreate it and focus on improvements. And the absolute localization layer of this pipeline was too undocumented and complex to recreate. It would take more time than I have for diploma, so I replaced it with WildMap. And for the future, this dataset will be updated to 100 kilometers with more frame rate, so I can experiment with this parameter as well and proceed with my research further on the hybrid pipeline. So in summary, there was established a framework for 10 plus methods across 4 families on 10-kilometer flights, exposed dominant failure modes, and no single method proven like better than others. So it motivated the hybrid fusion pipeline to be researched. And thank you for your attention.
Questions, Rostislav?
Yeah, you mentioned that you excluded superglue because it has non-commercial license, but are you doing commercial research?
There was some.
Why don't we get any?
There was some piece
royalties?
They didn't posted the full repository for the localization. The pieces was missing, and they explained it that we cannot because of the license. I don't remember what was the deal because it was 2 months ago, but there was some missing pieces with it.
Maybe online audience, if you have questions, you can raise your hand, unmute microphone, and ask.
Then, if we still have time.
I
So, yeah, certainly your preliminary analysis shows that you have to do hybrid, to use hybrid methods. And do you already have an idea, for instance, is it like you'll use this satellite imagery for absolute localization every minute of fly, or is there any other pipeline?
The current pipeline is a startup fusion. I didn't include its description as it's a part of the future work, not as the position paper, but it combines as a basic optical flow, which is high frame update. The XFIT method that we saw on the frame, as it's the best method for the edge deployment and it performs relatively well. And also the DIMA-based absolute localization pipeline, it's all fused via the Kalman filter. So feature matcher and optical flows, they have pre-fusion before Kalman filter to be the main source of update. It's about like half of the hertz or something like this. And the absolute localization with retrospective updates on Kalman filter 1 time per 2 seconds. Something like this. So
it's another hyperparameter you can actually.
Yeah, and then Kalman filter based on confidence it decides whether to even trust this method updates or to rely on like some inertia.
I have maybe it's not very essential, but quick comment. In one table it was hybrid fusion called, like category called hybrid fusion. In my opinion, this is two like synonyms, and you can just maybe call it fusion or hybrid methods. But this is just a comment. And another question is: do this sublog fusion does this sublog fusion work actually test real deployment, or is it also on a synthetic data?
As they have their own dataset, which is also called Subtle Fusion. They test on RLVL, as far as I remember, each Chinese dataset. I tested parts of my pipeline on RLVL datasets, so I have like this point of contact between paper and my implementation. So I can see how much my implementation better was than what they stated on that small flights on RLVL. And they promised to release the paper on October 25, but they didn't. So I also contacted them, but they didn't respond.
Yeah.
I don't know.
I just again looked at the image figure, and everything is mathematically correct because you say that it's east and goes with negative value. So it's indeed this is direction to the east, but that is to the to the north because it is with negative numbers. But maybe it makes sense to flip it and show east this way and north that way.
Yeah, I guess I just split them for the method and I missed this point during plotting. Yes, thank you.
Okay, thank you.
Thank you.
Next presenter is Dmitry Uzer. He's We will be presenting work entitled Self-Supervised Satellite Imagery Encoder for Location Retrieval. Okay. Yes, sir.
Hi everyone. I'd like to present my short position paper for my thesis. The topic of my thesis is self-supervised satellite imagery encoder for location retrieval. I am advised by Mark Jan, he's a PhD student at Ukrainian Catholic University. Let's start with the plan of my talk. I'll talk about motivation, the research goal, the background of my research. This section will include like findings from my literature review and just like reflection on the topic. Then I'll talk about research gap, questions, and hypotheses, suggested approach, research plan, and summary. So let's start with motivation. My colleagues have already talked about it quite a lot. And the motivation is pretty clear here. GPS is denied in active war zone, and navigating UAVs in such zones is a critical challenge. So visual geolocalization can help support existing navigational systems. And the thing is that the training data for this kind of task is pretty limited. But there is a very small amount of paired UV satellite data sets, and satellite-only data is abundant. Like we have a lot of pictures of our planet, so it's there. And the core challenge for my project is, for my research, is to address the main gap between UAV and satellite images, because they are quite different. And the cross-view domain gap is pretty critical. And due to this gap, using satellite-only data is hard. So my research goal is to learn robust representations for UAV to satellite localization. And the idea behind it, to achieve this goal, is to use abundant satellite data for self-supervised training to close the domain gap between UAV and satellite imagery. So the ground for this research is we can formalize this task of geolocalization as retrieval. The task is reduced to a representation learning problem, and use UAV images as queries, comparing against the database of satellite images, which is generated ahead of time and stored on notification. And we encode UAV imagery on the file from the drone. Most current SOTA methods need paired UAV satellite training sets, and is primarily dominated by supervised methods. And classic benchmarks for this kind of task are reaching saturation and are considered as solved. And currently we are at the point where new kind of benchmarks are rising, like in the most recent work, which I will be talking about. So the existing research, I'll go through this quickly. Classical approaches require valuable data. An example of such methods is NetFlat. This is the classical approach to visual face recognition task. It is more adapted for like street view cross retrieval, but can be applied here as well. And geospatial foundation models are rising. These are like foundation models that use self-supervised learning techniques to build rich internal representations, which can be later applied to downstream tasks. These approaches include contrastive losses, contrastive objectives like GSSL, SACO, Chroma, which use like temporal or cross-model positive pairs, mask image modeling, submine, scale line, DOFA, self-distillation, using like Dino V2, Dino V3, which is like still unexplored right now in public research, but there is a key finding that such models, geospatial foundational models, they do not consistently outperform supervised baselines yet. This is the core finding from the very amazing work on Pangea benchmark, which is basically like meta-analysis of the domain from the last year, I think, or the year before. And this basically like concludes that performance derives for such foundational models across domains, sensor modalities, and regions. And that's where I arrived during my research review. Initially, I wanted to start with just like using some mainstream backbone for SSL and evaluate the results. But I found out that in the recent years, diffusion models are kind of like there is a new idea that diffusion models can be used for downstream tasks, not just for generative tasks, because they generate images by denoising source images and the noise, vice versa. And as a result, they can build rich internal representations that can be used for downstream tasks. They have multi-scale features given to the classic net architecture, which captures features at different sizes. And the emergent behaviors of such networks can be used for discriminating tests. In the field of geospatial imagery, diffusion set is the, I guess, like go-to choice for now. Like it is the most recent diffusion model for geoimagery. It is a stable diffusion that was fine-tuned on satellite imagery. And there is a recent study of set diffuser, which applies this model to various range of discriminative tests using like some advanced feature fusion approaches. And they cover all the tasks from classification to segmentation, but they miss out on the most like obvious one of retrieval, which is used for geolocalization. So there are like no retrieval experiments that use diffusion models for this task. That is why like I chosen this research path I'd like to explore. The thing is like diffusion-based representations are underexplored for cross-view geolocalization, and no such prior work exists. One research hypothesis are cross-view robustness via fine-tuning, which is like basically the self-supervised fine-tuning of this foundational model with UAV view augmentations will yield embeddings more robust to UV satellite viewpoint difference, scale, and appearance gap than no fine-tuning, like zero shot, and established models in this field that are like Flip and Dino-based and others, as measured by recall-at-home, because this is a retrieval task. And my second hypothesis is satellite-only training is sufficient, that satellite-only data is enough for this task. So the general vision to my approach is a end-to-end UAV geolocalization pipeline. UAV captures an image in flight, produces query image encodes. You get an embedding, retrieve the closest satellite tile that was previously encoded, and then infer GPS coordinates for UAV. Trajectory level consistency. We can reconstruct the flight path from sequential retrievals and evaluate this with Frechet distance between the predicted and the truth trajectory, which is like, I would say it is a segue, like it is future work, but yeah. And feature extension to this retrieval task for sub-meter accuracy is to feature match use superpoint or current matchers that exist, and compress and distill the model because in the end we want to have a edge deployed model that is capable of like real-time geolocalization, and diffusion models are pretty large. But this is an engineering flow, and this research mainly focuses on novel research. So I approach this task in 3 stages. Establish a satellite baseline, basically like validate the pipeline for this for diffusion set application. Then run a zero-shot UV to satellite retrieval. It went bad, like 3% recall at 1, just at a time. And stage 3 is self-supervised fine-tuning, which uses a adapted Havel protocol, which has been like introduced as a preprint like in December, I think, and it is work from French colleagues, and they introduced a huge novel complex benchmark along with their work, and they approach like beats all existing state-of-the-art models. Yeah, and like recently they presented their work at so this approach features like using satellite images, generating UV view simulated views from these images, and they use spatial non-contrastive objective by generating like a couple of augmentations and comparing. I'm going to be using SSL for EO stealth dataset. This is Sentinel dataset wrapped for like self-supervised learning. And I will be adding like additional fine-tuning steps because the important additional cable is using uncanny filters on satellite and UAV images to bridge the domain gap. I cannot do that because I have like a predefined backbone, but I will do that as an additional loss for reconstructing canny filtered images of UAV source images, and then I will test my hypothesis. So just to save some time, I will go ahead and skip this slide. My approach will be evaluated on the UAV swap dataset. It is pretty like accessible. It has diverse reward scenarios, and it has like multiple UAV flights. And also SUS 200 dataset and dense UAV dataset. Metrics I'm going to be using is recall at 1 because it's retrieval and probably Frechet distance in the future, just like for comparison. The contribution and impact of this work is opening the question of whether such exotic models can be used for retrieval tasks in satellite imagery and exactly for visual face recognition setting. And this is one of the early applications of such models to this task. Also, sort of supervised fine-tuning pipeline for the diffusion set model, or maybe stable diffusion, I'm not sure yet, but yeah. And if the hypothesis holds, this establishes diffusion-based representations as a viable and potentially superior alternative to existing baselines. So my research plan, this was like established 2 months ago. In February, I plan to do stage 1 and stage 2, basically like establishing baselines, pipelines, collecting data, and so on. In March, transitioned to stage 3, fine-tuning pipeline, performing experiments, all the fun of this work. And in April, I plan to conduct final experiments, results aggregation, and results validation. This is like just a quick illustration of how the embeddings look for one UV flight from UV with log dataset. The red ones are UV images, the blue ones are satellite images of chunks, and you can see like the clear clusters between them. The lines are like connections towards between the chunks and images from UAV. And this is just some show of like some super extra early training. Basically, like we can see that the clusters are coming together in some sense. But this was like just a couple of epochs that for self-supervised learning is pretty like not a lot. But yeah, it's just like showing some promising signs. So this is a summary of the approach. I defined what it is, this three-stage pipeline, and yeah. So this is it. Thank you for your attention.
So we mentioned this paper, CI and UV health. Do you see any disadvantages because they said they outperform everything? So other admins in their approach, like in some cases, you can more like more.
Do you mean like in the paper that there are some conditions when it works worse?
So as I understood, you kind of adopt their approach to your models. And can we use this approach in any conditions other than not hard cases?
Yes, yeah, I think so. I guess like the main contribution of that approach is the data set, because like their data is pretty good and is better than any like public data set available. That's why like they state they are state of the art approach. Yeah. Their findings are interesting.
So you said, you said that March was going to be the most funny month of your research, was it? Did you do all the planned steps?
Yeah. But I guess like I did stage 1 and stage 2 at the beginning of the March, and stage 3 like maintaining stuff. I started doing it like in the middle of the month.
Okay.
Yeah.
And a more serious question. Look, if you are aiming at a model, at solution which is going to work on the front line, then there is one important problem, that the satellite imagery is going to be outdated. So the scenery on the front line unfortunately changes, and the cities are constantly damaged. And so the most important landmarks which you can get on the satellite imagery gets lost.
That's a good point. But like I'm doing this work like this is not supposed to be deployed in the front lines where the landscape is constantly changing. Like this research is focused at
the Kremlin.
Yeah.
Okay.
Like this strikes. Yeah.
I also have a question. How sensitive is the approach to changes in camera resolution and so on? Because okay, we may have static satellite images, or we may choose say satellite image provider and work with it, but what about drones?
Yeah, that's a good question as well. I guess like this is some future work, and you can tune the whole approach to like there is this additional step of distillating the model and like adapting it for edge deployment, and then we can account for this like camera forensics difference and UAVs. But yeah, I thought about it in the beginning, but my advisor told me that it can be thought of later.
Okay, Roma, let's allow online audience ask and then wrap up.
Okay, thank you. Thank you for the presentation. I have a brief question kind of connected to what Ruslan asked. So did you consider the stabilization issues for the drone and the problem with matching the UAV plane and the satellite image plane? So they should kind of match for your fusion to work. So did you consider issues with stabilization and reconstruction of this plane?
Sorry, I didn't really hear the question.
Oh, okay. I can ask it in the chat then, and you answer there.
Okay, so I think let's move on, and Dmitry will answer in chat. Thank you. So the next work will be presented by Adriana Sulka, and the work is entitled Data Generation and Post-Estimation of Fixed Wing Drones. It's always funny to observe how master students struggle sharing the presentation. It's really
maybe someone who did like the Google presentation with notes can help me because I'm a bit lost.
Please, and where are the presentations?
No. I'm sharing this course.
No.
Okay, I will try to improvise, I guess.
Right.
Димар, какую презентацию сделали?
Я просто пресекаю. Ну, небезпечно.
Still like this.
Oh, okay.
Sorry, what was that? No. Then a nice option, sorry. Presentation.
Там есть такая кнопка, как Share Advanced Part Discussion.
That's the time that's
Okay. So thanks a lot, Ruslan.
It's not yet.
That's great success. Okay, so hello, fellow colleagues. My name is Adriana Sluka, and the topic of my presentation is data generation and post-estimation of fixed-wing drones, advised by Igor Frashin. So plan is as follows. We start with motivation and research goal, then go through analysis of related works, which will cover rigid body pose estimation methods, current state of the art, and approaches for synthetic data generation. Then we'll discuss research gaps, problem setting and objectives, planned approach, and what have been done so far. With the beginning of full-scale invasion of Russia in Ukraine, fixed-wing drones gained widespread use, mainly due to their ability to fly long distances with relatively low unit cost. As a result, the development of interceptor drones has advanced, and interceptor drone must have high level of target detection and tracking. Our hypothesis is that recovering objects 3D rotation and translation improves drone-to-drone tracking and interception pipelines. However, even though rigid body pose estimation is actively evolving field of computer vision, its application in drone-to-drone scenarios isn't explored, and the main blocker is the absence of openly available datasets with required annotation. Existing open datasets for 6D degrees of freedom pose estimation typically focuses on household objects, tabletop scenarios, and industrial parts. On this slide, you can see examples from the main benchmarking challenge for rigid body pose estimation and the evaluation data. So the general goal of this research is to establish a proof of concept baseline for existing models of rigid body pose estimation in fixed-wing drone settings. As a part of this, synthetic dataset for training will be created and the sim-to-real gap evaluation will be performed. Now about methods for pose estimation of rigid bodies. Family of classical methods focused on manual feature extractions such as point descriptors, edges, or contours. After emergence of depth sensors at the beginning of 2010s, the whole field shifted heavily towards RGBD images with depth channel. Advances in deep learning for image classification and object detection after AlexNet motivated the adoption of learning-based approaches for pose estimation. Manual feature extraction was replaced with implicitly learned features. Methods can be divided in next subgroups. Direct parameters regression aims to directly regress object poses as 3D rotations and 3D translations using features implicitly learned with CNNs. Discrete 3D viewpoint classification takes an entirely different approach, treating pose estimation as classification problem, not the regression one. Rotation space of an object is discretized into bins of viewpoints, where each point is considered a different class. Key points localization methods rely on 3D objects' key points and their projections in 2D. Key points may be either bound in box corners or have semantic meaning. But the obvious drawback of having few key points responsible for pose estimation, for example, 8 for bounding boxes, slightly more for semantic key points, is that occluding 2 or 3 of them ends in a considerable loss of information. That's why dense correspondence methods were presented, and the strategy is to retain as much information as possible and avoid limiting decision-making to a small number of points. These methods return location of each pixel from an image on the corresponding 3D model of an object, which preserves much more information for the final decision. And the trend of the last few years are foundational models. They're heavily inspired by the progress made in the field of detection and segmentations by models such as Dino V2, SAM, and Cleve. The goal is to create models that perform well on out-of-train objects during inference. Currently, they are placed at the top of leaderboards on main benchmark for 6D object pose estimation, the BOP challenge. Inherently, they are hybrid models. A little bit about state-of-the-art situation. BOP Challenge is the main competition platform for pose estimation models. Evaluation is performed via average recall, where averaging happens over a few datasets. You can see this here on the column average recall core. And current situation with state-of-the-art is a little tricky because highest results on leaderboards are mostly achieved with unpublished models. For example, the top 5 places are by the model WAPR, and this is the same author, and he is fully anonymous and didn't publish anything. And with RGBD images. For example, here the first RGB model appears only on the 17th place. So after reviewing the leaderboard, we have chosen 3 models for our state-of-the-art evaluation. These are HCC ePose and Zebra Pose, both with efficient NetB4 backbone. They work with RGB images and have open source published code. Now a little about synthetic data generation. With deep learning evolution arises question about large unlabeled datasets. First and most naive method is called render and paste approach, where no physics or common sense is required during generation. It allowed to create large volumes of data back in the days, but highlighted the problem of sim-to-real gap. Alternative approach is physically based rendering, which aims to create images that look real. It takes into account physics of the objects, world, and light. And the polar opposite paradigm to PBR is domain randomization, where core idea is to use heavy augmentations and make real-world data look just like another variation. It forces neural net to be robust to the features that are not meaningful for the task. As a result of related work review, we defined 2 research gaps. Pose estimation in fixed-wing drone setting hasn't been performed yet, as the field is heavily concentrated on everyday use cases, which results in absence of such narrowly specialized dataset. We set our problem as, given a single RGB image I, camera intrinsics K, and the 3D computer-aided design model of the drone, estimate drone pose, rotation R, and translation T in the camera coordinate frame. With research objectives listed on the slide. 1. Generate a large, at least 10,000 images dataset of RGB images using PBR and domain randomization approaches. Retrain and evaluate existing state-of-the-art methods that work with RGB-only inputs on synthetic data. 3. Manually prepare and annotate a real image subset to enable evaluation under conditions of missing camera intrinsics. And 4. Evaluate the retrained models on the manually annotated real image data. And now a little bit about our approaches. For synthetic data generation, we will use Isaac Sim from NVIDIA, as most of the papers in the last few years use this setup for the training data preparation. It supports both PBR and domain randomization techniques. And for background randomization, a few sources will be used. For example, 3D worlds generated via Marble World Labs AI, regular RGB images of different outside sceneries, and panorama HDRI images. Primary state-of-the-art evaluation will be conducted on generated images, as with synthetic data, we already set the camera intrinsics during generation. The models to use first are HCC, ePose, BF, and Zebra Pose with efficient NetB4 backbone, as they are provided with open source. And this approach removes most of the frictions for initial benchmarking. To make results comparable to values on the benchmark for 6D object pose estimation, we will use average recall metric in the same style as they use on the leaderboard. This is the average recall over 3 other average recalls with 3 metrics: maximum symmetry aware surface distance, maximum symmetry aware projection distance, and visual surface discrepancy. However, the last one is under consideration, as it probably we will need for this the depth channel on evaluation images, and I'm not sure that we will be able to obtain it. And for easier interpretability, as an intermediate metric, we will use ADD, average distance of model points. Camera intrinsics matrix is a key component for pose estimation from image task. It maps 3D scene onto 2D image plane, thereby enabling the recovery of object rotation and translation. If for generated data, camera intrinsics are set during generation, then for real-world data, we don't know them usually, and these parameters need to be learned or approximated. When a video sequence is available, we can use structure from motion methods, for example, call-map. However, there is risk that call-map will not work well with the highly dynamic parts of the video. That's why we took into consideration Anycam, which is a transformer-based model that allegedly can extract intrinsics even from dynamic camera sequence. Intrinsics is focal length, and principal point will be estimated as the center of an image. And after the camera intrinsics are extracted, a real-world data can be annotated using software like Blender or NVIDIA Isaac Sim, and annotation will be manual and performed by the author. Then retrained state-of-the-art models will be evaluated on an annotated set of images. Early results. So far, we have chosen the fixed-wing drone model. This is Skywalker X8, and we have obtained the computer-aided design model of this drone, as well as open source YouTube videos of the same drone, both with aerial and ground footage. These are screenshots from the videos. And we have established the pipeline for synthetic data generation with domain randomization applied. And 2 examples you can see here. The background that is used on these images is the 3D world generated with AI by Marble World Labs. Many thanks for your time. І дякую за увагу.
Sorry, I was silent through the whole day. Now I have a lot of questions. My first question is about the intended contributions of the project. Could you please
Okay, so yes, so the intended contribution is dataset. I'm not sure that it will be open source, but it can be used for the initial benchmarking of the problem of pose estimation of fixed wing drones. And as I said in the beginning, this is a proof of concept. So it just to understand if there is sense to dig deeper in this problem with more resources potential.
Thank you for giving that pass to my second question. What is the problem you are going to solve?
Problem we are going to solve is the rigid body pose estimation problem on fixed wing drones. So our hypothesis is that, for example, some drones might have like more vulnerable places on some part of the drone, if you understand what I mean. Like it might be more effective to strike it, for example, from the bottom. And to understand it, you need the drone interceptor needs to understand how the target drone is rotated in the space.
How does this data set?
Huh?
How does the data set you collect help better estimate the pose?
As far as I'm concerned, this approach hasn't been tested. So like we don't know how the existing methods will shift, like domain shift, how it will happen. So the data set is the starting point to check this hypothesis to understand if it even makes sense to explore more.
Okay,
You mentioned a few sort of models for pose estimation. Are any of those prone to work good on edge devices?
This is out of scope of our research. Like we haven't, we are mostly fixated to see it, to make a proof of concept, yeah, basically.
Can you show the slide with those models?
Yes. Okay, no, the other slide, like.
Okay, I have another questions. No.
Yeah, now I have another question. Sorry, I missed the slides. So, don't you think those models are ancient to be used?
No, they're not. They're like 2024 year.
How many times per year such models change?
For example, we can take a look here. This is the leaderboard for a task of seeing objects. So date is the date where this model was uploaded, and as you can see in the leaderboard, there are like pretty old models that still were not like
just
beaten.
At the top, which says 2020. I'm sorry.
Yes, but I mean that, for example, the third place is still held by the model which was presented in 2023. So it's not that easy, like to beat some of them. They are not getting out of date as fast as we think.
Very good question, or maybe suggestion. You showed us simulation with the simulated ground.
Yes.
Why not using real? We have lots of real.
Yes.
footage
I will. As I've noted here, that for background randomization, RGB images also will be used.
Jana. And device that will include the selection in computer vision with the work towards scalable sequence aware UAV to satellite localization.
Okay, just a second, please, because my notebook is often
Rests in peace. Ruslan is curious.
Yeah. So, hello. As this session mostly focused on UAV, I hope you wouldn't be bored because some information will be repeated, but also I believe that something will be interesting for you. So basically, my name is Ivan Starovid, and the topic is towards scalable sequence-aware UAV to satellite localization, and my supervisor is Roman Rezantsev. And the first slide is motivation, of course. Why do we need to solve this problem? And as I believe everyone knows, GNSS can be unavailable and the natural system can be lived. So basically, when we try to find the position of drone, there are no other option. So just one option, actually, to match onboard images with the georeferenced imager. And the problem formulation is pretty simple. We have some UV images from one sequence, and we have satellite map with the coordinates split it into M tiles, and we want to find UV location. So contents would be as this. I would cover key challenges, existing approaches, research gaps and questions, research hypothesis and research plan. We will look into sequence-based model architecture, metrics and datasets, and some of early results. So key challenges are pretty obvious. Basically, when we compare satellite and UAV, we can have illumination variation as same as seasonal one. We can have attitude changes, viewpoint difference, repetitive structures, and that's like the biggest problem. So here we can have like forests, fields, and roads. And sometimes we can have computational constraints. So existing approaches, we can divide them to like three main things. First one is like single frame, which can be retrieval and paired UAV to satellite matching. And also there are some sequence-aware methods. So what is retrieval? Basically, retrieval is the approach when we extract embeddings from the model, like as a result of processing the image from the model and compare it with the pre-computed satellite embeddings. And key principle is that retrieval is kind of a ranking problem. So we want to find the closest embedding by the cosine similarity, for example. And basically, this problem goes from visual place recognition. And if we sum up, there are like three main rules, which is written on this slide. So first of all, metric learning is the best because our loss is ranking based loss. Also, we need to focus on training like with the soft positives, not just like hard positives, because locations are on the Earth, which isn't discrete. And ideally, we would like to add additional losses. So, which here is written like re-supervision. That can be like additional geometry, geometry-based losses, semantics, and metadata. For example, we could know how our camera is located on the drone. And here, what I want to demonstrate that training setup really matters. For example, here we can see different recalls for vision transformer-based model trained on dataset with only hard positives. After that, they switched to soft positives with in-compare and pair loss. And after that, they introduced their like fancy model, which only improves score on 2% compared to like almost like 20% just from switching loss. And also now we can switching from not switching but moving to large models. They are really popular in the retrieval problem, and one of them is Sardino, which is trained on satellite imagery. And the question, as I will explain later, is how well it can be transferred to UAV problem. And another approach is parity with satellite matching. So basically, to the model goes UAV image and satellite image, and as a result, we have probabilities for each location. So this one works better, of course, but it has some constraints, such as we require, so we need to know search region, and it doesn't scale well because we need to process whole map each time. And that's an example of such approach. So we have UAV image as an input, satellite image as an input, we have attention blocks, and as a result, we have allocation on this map. So when we talk about sequence-based methods, most of them also from visual place recognition. And there are like two main approaches. We can combine, if we talk about retrieval, we can combine embeddings to one embedding, for example, or we can do like post-fusion after using our retrieval model. And if you move to UAV domain, there are a lot of works about sequences, actually. And the most popular approach is to use, as we discussed today, is to use hybrid approach when we find location, global location, and after that apply template or feature matching and use pseudometry. So research gap is that current approach is focused on single frame UAV satellite matching. The impact of domain adapted representation, such as Sardino, is not well understood. Existing UAV sequences methods rely on trajectory modeling rather than Lorentz similarity. What I mean that some authors like have a set of sequences and they just looking for closest one, and this thing doesn't scale well. And last one is the main idea is that simple aggregation can beat or can be not much worse than like complex model. Okay, so research questions are connected. Can be about Sardino for this problem? Can we beat how much information we can get from simple sequence aggregations? And can we beat these simple aggregations by big model? And the hypotheses are that Sardino would be effectively aligned. Sequence aggregation would give much better scores than like just one retrieval. And yeah, generally that's it. So research plan is that we compare Sardino and Dino. We do compare single frame and different aggregation methods. We train our retrieval model, and after that we perform again like different aggregation techniques and see how better it became. So we extend this to different data sets and we compare it with like a complex approach. So what are approaches for aggregation? We can calculate similarity matrices. So we find similarities between each image and satellite images. For example, if we have 3 images as input, we would have 3 similarity matrices, and after that we can do mean absolute or probability-based aggregations, or we can learn some ways what is the best way to combine different similarity matrices and find the best location. And here is our fancy model, which uses attention over UAV sequence, and after that cross attention over UAV images and satellite images. And as loss, we use cross entropy loss, where each tile has probability based on distance from true location. Here we have matrix that's basically recall, spatial recall, which is recall at some distance, I mean median distance, and spatial distance matrix. This one is kind of hard to explain, but basically it looks at the position of image and the distance of this image. So we want our like first ranks images to have a closer position than like 10th and 20th ranks. About data sets, we have a lot of data sets. Some of them are mentioned today. I chose just like 3 which have sequences. First one is visual data set, which have like 11 regions with the sequences as strips, as shown here. Another one is RVL. This one is a little bit worse. What I mean, it doesn't have so the UAV information, so we don't know the angle, how we fly it, and so on. But this one has different like heights and different illumination changes, which can be used for validation of our results. And third one is subblock, which has just like 1 region, 3 sequences, because main part of this dataset is still closed. So this one is third one for validation. As about earlier results, we compared Dino with Sardino in 1-to-1 matching, and we showed that Sardino model, which is trained on aerial images, is much better than Dino model. So we have sign for aligned rotation and random rotations. And the interesting thing is that Sardino small model is better than big, like base one, bigger one, because it bigger one is trained more, like we can say that it's overtrained on aerial images. Yeah, it cites more patterns and it's harder to transfer it to UAV domain. So we can use the Sardino for fast adaptation and to test in different conditions. Also, we trained our baseline retrieval model based on intersection over union based loss. So for that, okay, sorry, I will show like this. We train it as follows. So we take pairs of true positive images and like true positives here is on diagonal. Here we have like for example, 10 satellite images, 10 UV images, and we want true positives to become like closer and negatives to become further. And as a result, we also got that like the soft positive strongness is much better than like training only with hard positives. Also, here is an example of max aggregation when we take a sequence of four UAVs and aggregate similarities matrices, and we take like biggest values for each tile and take it as like true location. And here is another example. So what I showed here is 1D projection of satellites embeddings, and we can see that by that way we can find where is the river, for example. And river is a big problem because, of course, for a river we can't predict like true location well. But of course, when we work with sequence, we can use this information and it's much easier. For example, if we were somewhere in this site before river, and we adopt our like sequence-based methods, we can predict location somewhere in the river. Yeah, so basically that's it. Yeah. So, okay. Questions? There are no.
I have a small question. Was it on Bastarina on slide 10?
No.
I have a further elaboration for this small question. So if it wasn't, what was the contribution of your project?
Yeah, it's just okay. So first of all, I cannot. I will add. Okay, where is it?
Slide 10. Nine.
Yeah. So this basically studying from the paper, but I would add the Bastarina is as well. A general contribution is that we explore different sequence aggregation techniques, and we ideally we show that like with a good retrieval model and not really hard aggregation, we can achieve like outstanding results, and we don't need like really hard model with attention. And if it's in some cases is better, we will show in some cases we need to use it, and in which not.
One more question. I think let's return to the Bastarina one.
Okay.
Do you have permission to use these bitmaps in your slides? What is the NAV license for this data set?
Okay, so I didn't extract these images by me. Here we have a link to the data set, so I believe as it's like cited, it's not a problem.
This link will lead us to where?
To paper.
To a paper. The paper has been written by them. Not by you.
No,
I suspect.
Yeah.
So do you have the permission from the authors of this paper to use their material here without any reference, any explicit reference?
Yeah, probably I will add that reference.
Probably this is a big mistake.
No more questions. Thank you, Ivan. We just completed the session 5 of the symposium, which is actually today's second session. And right now we have 26 minutes break, coffee break, and after that we will continue with the last session, also in computer vision. So I invite everyone to a lobby to have a coffee and a snack, and see you in 25 minutes here. Мгм. Спробуй собі включити шерінг, переконатися, що спрацює. Треба зайти в Zoom.
Recording in progress.
Але це що це не було, мене просто.